Deep within these ancient mountains lies the hidden source of the most powerful magnetic energy on Earth. Every day, hundreds of skilled workers arrive to begin the massive task of extracting rare earth minerals. Precision begins in the lab, where geologists identify the richest veins of neodymium hidden in the rock. Massive drilling rigs move into position to prepare the mountain for a series of controlled industrial explosions. Technicians carefully place specialized charges into the boreholes to ensure a perfect fragmentation of the ore. In a matter of seconds, the force of the blast breaks millions of years of geological history. As the dust clears, giant water cannons begin suppression to prepare the site for heavy excavation. Gigantic excavators load dozens of tons of raw ore into haul trucks bound for the processing plant. The journey to the refinery begins as these massive vehicles navigate the treacherous roads of the mine. Boulders are reduced to manageable stones in a primary crusher that exerts millions of pounds of force. A network of high-speed conveyors carries the crushed rock into the heart of the secondary milling facility. Inside these rotating steel drums, heavy balls grind the ore into a fine, sand-like consistency for processing. The fine powder now enters the chemical plant, where the complex separation of rare elements begins. In these reinforced tanks, concentrated acids are introduced to dissolve the minerals and release the neodymium ions. Precision chemical monitoring ensures the solution remains at the exact pH required for optimal mineral extraction. The complex process of solvent extraction begins, using organic compounds to isolate neodymium from other metals. Dozens of separation stages are required to reach the high levels of purity needed for industrial magnets. In the final tank, the neodymium ions are finally separated into a concentrated, pure liquid form. A chemical reagent is added to the liquid, causing the pure neodymium to precipitate as a solid. The white slurry is filtered through a vacuum system to remove the remaining liquid and isolate the material. The damp material is loaded into a high-temperature kiln to be converted into pure neodymium oxide. Intense heat triggers a chemical reaction that transforms the carbonate into a stable gray oxide powder. Once cooled, the oxide is ground into a uniform powder that will serve as the base for the alloy. Sealed drums of pure neodymium oxide are transported across the facility to the high-temperature foundry. To create the final magnetic alloy, precise amounts of pure iron and boron are prepared for melting. The raw materials are loaded into a vacuum induction furnace, where they will be melted together at extreme temperatures. The furnace is sealed and air is evacuated to prevent any oxygen from contaminating the delicate alloy. Powerful electromagnetic fields generate intense heat, melting the metals into a single, homogeneous liquid at 1600 degrees. The molten mixture is stirred electromagnetically to ensure the neodymium, iron, and boron are perfectly distributed. The liquid metal is poured onto a water-cooled rotating drum, instantly solidifying it into thin strips of alloy. The solid strips are placed in a hydrogen atmosphere, which causes the material to crumble into small flakes. High-pressure nitrogen jets pulverize the flakes into an ultra-fine powder with particles only a few microns wide. Because the powder is highly reactive, it must be stored in an inert nitrogen environment at all times. The canisters of refined powder are now transported to the press room for the critical alignment phase. A powerful magnetic field aligns the powder particles while a hydraulic press compacts them into a solid block. These freshly pressed blocks, known as green compacts, are fragile and must be handled with extreme care. A rack of green compacts is prepared for the sintering furnace, where heat will fuse the particles together. In a high vacuum environment, the blocks are heated to near melting temperatures to create a dense, solid material. For several hours, the magnets are held at precise temperatures as the atomic structures bond into a single piece. After the heat cycle, a controlled cooling phase prevents internal stresses from cracking the newly formed magnets. The sintering process has transformed the fragile powder blocks into incredibly dense and durable magnetic material. Industrial grinders with diamond-tipped wheels shape the magnets to the exact dimensions required for their final application. For complex shapes, high-precision wire electrical discharge machining is used to cut through the hardened material. Any residual dust or particles are removed in an ultrasonic bath to ensure a perfectly clean surface for coating. A protective layer of nickel is applied through electroplating to prevent corrosion and protect the magnet. A high-speed laser inspection system verifies that every magnet meets the strict dimensional tolerances required by engineers. Random samples are subjected to extreme pressure and heat to ensure they will not fail under industrial stress. Engineers measure the magnetic flux of each piece to ensure it possesses the exact power required for its niche. Though shaped and coated, the magnet is not yet magnetic. It must now pass through the final activation coil. A massive pulse of electrical energy permanently aligns the internal structure, creating an unstoppable magnetic force. Now fully charged, these blocks possess a dangerous attraction that requires highly specialized industrial handling equipment. Thick plastic spacers are quickly inserted between every single piece to prevent them from violently colliding. Without these crucial barriers, the sheer force of attraction would shatter the brittle metal into dangerous fragments. Each finished block undergoes a final visual inspection to guarantee the coating remains perfectly intact.
Automated robotic arms carefully transfer the stacked units into heavily reinforced industrial shipping containers. These specialized wooden crates contain hidden steel plates designed to absorb and contain the extreme magnetic fields. Workers secure the crates using solid brass fasteners to ensure the packaging stays fully structurally sound. A digital inventory system logs each specific batch, recording its exact power rating and dimensional data. Heavy foam inserts are added to the container to prevent any slight movement during the shipping process. The crates are firmly sealed shut, locking the raw power safely inside for the long journey. Warning labels are prominently applied to ensure everyone understands the invisible dangers hidden within the cargo. Every single package is weighed on a precision industrial scale to verify the final shipping manifest. The verified crates are wrapped in thick protective film, shielding them from moisture and environmental damage. Electric forklifts carefully lift the heavy wooden pallets, moving them steadily toward the main holding warehouse. In the sprawling storage facility, hundreds of completed pallets wait for specific wholesale distribution orders. Climate control systems maintain perfectly dry conditions, ensuring the protective nickel coating remains completely untarnished. A massive logistics dashboard tracks global inventory, directing workers to the precise locations of requested batches. When an order arrives, automated retrieval vehicles navigate the tall warehouse racks to collect the material. The robotic system seamlessly coordinates the extraction, pulling thousands of pounds of product without human intervention. The selected pallets are transported directly to the busy loading dock, ready for final worldwide dispatch. Heavy freight trucks arrive at the facility, their massive trailers built to handle extreme industrial weights. Dock workers coordinate the loading sequence, ensuring the heavy magnetic cargo is perfectly balanced inside the trailer. Industrial ratchets and thick steel chains are used to secure the pallets firmly against the truck bed. A final security sweep confirms the trailer is safe and the magnetic fields are properly contained. The heavy steel doors are locked and sealed with an official tamper-proof tracking tag. With the paperwork finalized, the massive freight truck pulls away from the factory and hits the highway. This cargo is destined for a major industrial client that manufactures highly efficient modern electric vehicle motors. The convoy travels across the country, carrying the invisible force that will power tomorrow's green vehicle technology. The journey continues through the night, monitored constantly by a dedicated satellite global tracking system. Dawn breaks as the heavily loaded truck approaches the sprawling complex of the electric motor assembly plant. The truck clears the security checkpoint and slowly reverses into the designated heavy receiving bay. Receiving technicians break the tight seal, opening the trailer to reveal the pristine wooden shipping crates. A heavy-duty forklift unloads the pallets, moving them quickly onto the factory's bustling receiving floor. Quality assurance inspectors verify the batch numbers, confirming the exact specifications required for the assembly line. Workers utilize specialized tools to carefully break the brass fasteners and open the heavily reinforced crates. Inside, the dense layers of packaging are removed to expose the perfectly protected and separated magnets. Using brass hoists, the heavy stacks are lifted and transferred directly to the motor assembly station. Engineers prepare a massive steel rotor, the central spinning component of a high-performance electric engine. The entire workspace is kept free of loose ferrous metals to prevent sudden, dangerous magnetic accidents. Powerful electroelectric allies grasp the individual magnets, overcoming their immense attractive pull with pure mechanical strength. With pinpoint accuracy, the robot presses the first powerful block directly into the steel rotor housing. Specialized industrial adhesives are applied simultaneously, locking the magnet permanently into its highly calculated, precise position. A massive hydraulic press applies tons of downward force to ensure the piece sits perfectly flush. The rotor is indexed slightly, exposing the next empty slot for another piece of the magnetic puzzle. Piece by piece, the robotic assembly line populates the entire circumference of the heavy steel rotor. As more magnets are added, the surrounding magnetic field grows stronger, requiring even greater mechanical control. A rigid carbon fiber sleeve is carefully fitted over the completed rotor to contain intense centrifugal forces. The fully assembled rotor is placed into a balancing machine, spinning at incredibly high speeds for testing. Sensors monitor the vibration levels, ensuring perfectly smooth rotation under the extreme demands of an electric vehicle. The balanced unit is finally passed down the line, ready to be installed inside the motor casing. The magnetic rotor must be paired with a copper-wound stator to generate motion. Mating the magnetic core into the tight copper housing requires flawless mechanical precision. A heavy aluminum casing seals the internal components, protecting them from moisture and dirt. Each assembled motor faces rigorous testing on a dynamometer to verify its maximum torque output. Completed motors leave the facility, heading directly to an advanced electric vehicle manufacturing line. At the automotive plant, these incredibly powerful motors are integrated into modern vehicle chassis. Robotic arms seamlessly bolt the heavy drive unit onto the vehicle's low skateboard battery platform. The painted steel body is lowered onto the chassis, completely hiding the powerful magnetic heart. Final quality checks ensure the electric vehicle is ready to deliver instant, silent power. Finished cars roll off the assembly line, ready to transform how humanity travels the globe. Inside a bright showroom, the final product waits for a driver to experience its capabilities. A new owner takes the keys, unaware of the intense industrial journey behind the machine. Pushing the start button awakens the magnetic forces, providing instant energy without a single drop of fuel. On the open highway, the Neodymium magnets deliver instant torque for perfectly smooth, breathtaking acceleration. When braking, the motor reverses its magnetic polarity, sending generated electricity back into the battery. Discovered in 1885 by Karl Auer von Welsbach, this element finally reached its full potential. By mixing neodymium, iron, and boron, these units are drastically smaller and lighter than traditional ferrite. From giant wind turbines to simple audio headphones, this magnetic alloy powers our connected modern world. It is an invisible force that quietly drives electric vehicles, data centers, and advanced global automation. What began as dusty rock deep underground is now the invisible force pushing humanity forward.